In the last lecture, we went through the basics of semiconductor heterostructure, the formation of semiconductor quantum bells, and how you join or sandwich two semiconducting materials to form the proper interface to get the well, and how the lattice match interface are actually made. In this lecture, we will look into some of the transport properties or specialities of this semiconductor heterostructure, because these heterostructures form the host or basis for a variety of devices that we are going to discuss during this lecture series. Okay, so today in this lecture we will do the carrier mobility and scattering mechanisms of charge carriers and the importance of that, and the difference between bulk and remote doping, the formation of two-dimensional electron gas, and some technology, very briefly, how you make quantum devices on these two-dimensional electron systems or electron gas. Now, the carrier mobility and the importance of the carrier mobility in the context of quantum transport. Okay. So, we know from the basic transport equation, that is the Ohm's law, that the current density is given by this relation, where sigma, that is ne square tau by m, is the conductivity, and E is the electric field, and J is the current density. So the sigma, the conductance, is given by Ne and mu, where mu is the mobility. Mu is the mobility. And this mobility is nothing but the proportionality constant between the average velocity the charge carriers acquire under the application of an electric field E. So mobility relates the terminal velocity that the charge carriers such as electrons or holes acquire under the application of an electric field. And if you look at the mobility formula, you will see that there is something called tau, that is the scattering time. Okay, scattering time. Scattering time, tau. Now, the terminal velocity that the charge carriers acquire depends upon how long they get accelerated under the action of an electric field. That is the scattering time, because the moment it undergoes a scattering, that acceleration stops and the momentum and the velocity resets. So, less the number of scattering events, more the mobility, or less the number of scattering events, more the scattering time. Scattering time is the time between two scattering events, and more the mobility. Okay. So, the mobility killer is a scattering time. Okay. And this table here summarizes the best mobility values that has been measured, that has been observed for various systems. The two-dimensional electron gas system, aluminum gallium arsenide heterostructures, are the best so far, and they have close to like a few tens of millions. Whereas the graphene, which is the later generation, that is a perfectly two-dimensional material system, that is also pretty nice, pretty close, the 200,000. The units are centimeter square per volt second. And when you come to the normal semiconducting materials such as silicon, it is pretty low. And the metals, it's even lower. Okay. So, the scattering mechanisms are very, very important to reduce the scattering centers. That is crucial for the observation of various interesting properties. So they are basically controlled by many of these scattering events. Okay, so scattering reasons. For example, there are various scattering mechanisms which affects the mobility. Here I have listed most of the common ones. So ionized impurity scattering. You will have impurity in the material in the form of dopants, such as donor or acceptors, or some of the impurities which are already got incorporated during the growth. Okay, these will get ionized, and those charge centers, the positively or negatively charged charge center, can interact with the electrons or holes in the system, and that can deflect or reset its path or change its path. That is a major reason for the deterioration of the mobility in bulk materials. Okay. Now, another major contributor to scattering is the phonon scattering. Phonons are kind of virtual particles. They can collide. Those are the quanta of lattice vibration. They can collide with or they can impart or take momentum from the charge carriers such as electrons or holes and scatter it. So these phonons are actually generated by temperature or lattice vibration. Also, higher temperature you have lot more phonons than lower temperature. This phonon scattering is a strong function of temperature. So you have lower and lower mobility and higher temperature. And that is the reason why you get a higher conductivity at lower temperature for metals. If you plot the temperature versus conductivity or resistance, metals will have higher resistance at higher temperature or lower resistance at lower temperature. That is mostly because of the phonon contribution to the scattering. Because the mobility deteriorates, the conductivity goes down. That is the relation. Then there is a third reason which is generally found in compound semiconductors such as gallium arsenide, where the system lacks the symmetry, and you'll have piezoelectric behavior in this material. So that can have electric fields distribution inside because of the lack of symmetry, which actually can scatter the charge carriers. These can be crucial. The scattering mechanism can be crucial or can be very bad at lower temperature, because where other scattering mechanisms such as phonon scattering is pretty much absent, because at lower temperature phonons are almost dead. Then you can have surface reference scattering. That's because of the step edge and various kind of roughness, which are going to act like scattering centers. Okay, those are really really crucial for two-dimensional system, because two-dimensional system means it's mostly surface. You are at the interface of between two material or at the surface of certain material. So the surface roughness, the quality of surface, the defects and dislocations of the surface between two material system, that can deteriorate your mobility like anything. So the surface roughness scattering is really really bad or is crucial. To reduce the surface roughness is really really important to get high mobility electron systems, especially two-dimensional systems. That is where the perfect lattice match growth is very very important to realize good quality electron systems. Then you can also have electron-electron scattering, which is significant at really high densities. All right. Now let us look into the role of mobility and dimensionality in observing the quantization. What I have here is a three-dimensional box with length Lx, Ly and Lz such that Lx is greater than Ly and greater than Lz. So from the simple particle in a box problem, you can say that the energy along these three directions, that is the energy quantization, is given by these three illustration. For example, in the Ex component quantization, they are close by because Lx is larger, Ey is slightly further, and Ez is even further. The levels are even further. And the total energy, that is Ex plus Ey plus Ez, is given by this. Okay, that's what it is. Now, you might ask, what is the point here? What is the importance? Now, the quantization means or observation of quantum transport feature, which we have discussed in one of the introductory lectures, is depending on these length scales, how they compare the dimension of the system. So the elastic scattering length, Fermi wave vector, and the inelastic or phase coherence scattering length. Okay. These comparison of these scattering lengths with the dimensional system, that is L, decides whether you will observe a quantization or not. Okay. For example, in this case, the energy scales in the Lx is so close by, so your scattering length need to be as large as the Lx or even larger to observe ballistic quantum transport. Okay. So you can still observe diffusive quantum transport. That is still possible. Okay. But for that, you need to satisfy this condition. Okay. But to have quantization in the other direction, you need to have a scattering length which is comparable to the Ly, which is shorter than Lx, and Lz, which is the shortest. So you can observe the quantization in that direction much easier than Lx or Ly. Now, the elastic mean free path and all the scattering lengths depends on the frequency of scattering events, which is basically decided by the mobility of system, because mobility of system is high when there are less number of scattering events. There are more time for these charge carriers to travel through the system unaffected. So if there is more time, it will travel more length, then it actually can move through the system without scattering. If that length, the mean free path, LE, larger mean free path you get when you have higher mobility or lower scattering events. So observation of this quantization depends on dimensionality and also on the mobility. So the dependence on dimensionality comes through the mobility. So if you have really high mobility, you can observe quantization with larger dimensions of the system. That is the point. So the point here is, to observe quantization, you need larger mean free path, you need higher mobility. You need less number of scattering events. That is the take home message. Okay. Now, we discussed that carrier mobility, one of the major factor which controls carrier mobility is the impurity scattering. The major source of impurity in the semiconductor is the dopant. The N-type and the P-type dopant in a normal semiconductor. Here I am discussing about the bulk semiconductor. Okay. Now, in the bulk semiconductor, you have, depending upon doping level, you have various scattering centers. We have many scattering centers if we have more dopants. But if you have less dopants, you have less scattering center, but you have very low conductivity, because conductivity is a function of charge concentration or carrier concentration and also mobility. So depending upon what application you are going to aim at, whether your eventual aim is to have really high conducting material, but you are not really worried about the mobility, then you can put more dopants. But then you will not observe any quantum mechanical events or quantum mechanical phenomena, because your mobility is very bad, because you pump a lot of dopants, a lot of electrons in the system, but there's so many scattering events. Then the observation of quantum phenomena at any nominal, at any reasonable size scale is almost impossible that you can make. On the other hand, if you put far less number of scattering, far less number of impurity, then you have, of course, you can get a higher mobility. But again, mobility is also controlled by the phonon scattering. So you have to wait until low temperature, but at low temperature you have far less carrier concentration, because these carriers need to come from the valency band, the conduction band for N-type. Okay. Then what that means is you have absolutely no conductivity, it will freeze. You will not have any carriers. So it's actually a very tricky situation. This plot here is telling you how the Hall and electron mobilities actually vary in silicon. So as we have seen in one of the previous slides, the mist mobility is like if you like a few hundreds above 1000, and of course the Hall mobility is lower than the electron mobility. That is also easy to understand, because mobility is mu is E tau by m, where m is effective mass, and effective mass for holes is higher than that of electron. So the Hall mobility will be naturally low. You can think of like, to move a hole you have to move n-1 electrons through the band, because a hole equal to 1 missing electron. So you are moving one hole in one direction, that means you are moving the rest of the electrons other direction. You can think something like that, but that's a good analogy, but that is how you can visualize why the Hall mobility is much lower compared to the electron mobility. But now there are some other material system where you can have really high mobility for charge carriers. Of course, mobility depends upon the effective mass, so you can choose materials with a really small effective mass. Gallium arsenide is one example. That is why a lot of lot of high mobility transistors are made by gallium arsenide. But there is a completely different class of material that is called the heterostructure we just discussed. There, you can have something called remote doping. So whatever this impurity scattering that we discussed, those come from the bulk doping. That means you are putting the dopants in the same space as where the charge carriers are moving. That means you put in the bulk, the dopants are in the bulk, and charge carriers also moving in the same place. But remote doping is something else where you dope somewhere else, but charge carriers will end up somewhere else, some other place. So the charge carriers moving space is specially separated from the dopants. That is possible in a quantum well. Here is an example where this side you can think this is like a aluminum gallium arsenide side, and this is the gallium arsenide side. Okay, so we discussed how do we get a quantum well in this case in one of the previous lectures. So you get a quantum well at the interface. Okay, so this is your aluminum gallium arsenide, and this is the gallium arsenide, and you can again have aluminum gallium arsenide. Okay, that is not relevant for this discussion, but at this interface you get a quantum well, but the carriers for this quantum well are electrons, but they are generated by dopants which are sitting somewhere else at certain distance away from the quantum well. So what happens is, if you remember the band structure, the conduction band of gallium arsenide is above that of gallium arsenide. So the conduction band of aluminum gallium arsenide is above that of gallium arsenide. The electrons can spill over. But now there is a potential barrier here. So these electrons which are spilled over here, they cannot go back because of the barrier. Okay. But now the triangular well will hold these electrons, and these electrons will be pulled by these ionized dopants here. There are dopants from where these electrons came. They will try to pull the electrons back, but they cannot go because of the barrier. So the electrons will be almost like pasted onto the wall. Kind of, it's not pasted, but it's moving very close to the wall. Okay, but they are moving in a space where there are no dopants. So they have really high mobility. That is the mobility that we discussed in one of the previous lecture, where the gallium arsenide, aluminum gallium arsenide heterostructure can have a few millions, tens of millions in mobility because of this remote doping. But you don't dope where the carriers move, you dope remotely. But the charge carriers, after ionization of these dopants, will end up somewhere else. That is the idea. This plot is telling you how the technology has evolved over the years. This is a bulk material, and this is one of the first 2-dig material happen in two-dimensional electron gas, which I will discuss in a minute. This is one of the first heterostructure. Then how this mobility has improved over the years, and in 1989 itself you will have like tens of million in mobility, electron mobility in these systems. This is the bulk mobility, and this is the temperature, and you can see that the mobility is pretty flat over temperature. It's not changing very much, even though it's a semiconductor. Okay. So this technology of remote doping is the key, or is the game change, was the game changer in the observation of various quantum phenomena in transport. And the remote doping technology is possible only in these heterostructures, because you need a place We need a specially confined space where the electrons move, which is separate from the dopant layer. All right. Now, I have spelled out the two-dimensional electron gas, or 2DEC in short, in a couple of previous lectures. But let us now define what it is. So this is the type 1 gallium arsenide, aluminum gallium arsenide heterojunction, and this is the quantum well. And we explained the previous slide that the dopants are sitting somewhere else, okay, and the electrons will end up somewhere else, okay. The electrons are here, okay. Now you can play around with the number of dopants, doping level, and all the other parameters or the growth parameters, and you can make this triangular well here. Let me draw this triangular well alone, something like this, okay, where the Fermi level goes through here. This Fermi level is defined by the number of electrons and dopants, okay, and the dopants are here. This is the gallium arsenide side, and this is the aluminum gallium arsenide side. Aluminum gallium arsenide side. Now you you engineer, because you can grow atom by atom, layer by layer, using technologies such as molecular beam epitaxy or chemical or MOCVD, metal organic chemical vapor deposition. So you can put right number of dopants and put right number of electrons, because dopants will ionize, so that only the first level, I would say, this is the EZ direction, so E1Z, okay, is populated. Because Z direction, the well is so thin, so the next level comes much above, because that we also learned that then the dimension is so small, the next level is further up. But next level is somewhere here, then somewhere here, but the Fermi level is here, so that level is not accessible, it's not populated. So you have only one energy level, or there is only one KEZ. There's only one momentum state below the Fermi level in the Z direction accessible. What that means is the motion in the Z direction is arrested or is forbidden, or of course now we are comparing with the Fermi wavelength and the scattering length on all the other parameters which defines dimensionality. So those things are much larger compared to the thickness of the well, the width of the well. What that means is, in that Z direction, the electron is actually the levels are completely quantized. There are no scattering events, okay. But other direction is a sheet, just like shown here. Just like here, this other direction sheet. The Z direction, which is vertical, it is a thin sheet of electron, where in the Z direction there is no motion possible. That means what you got is a two-dimensional sheet of electrons, where the electrons are confined to move only in the sheet. The third direction, the Z direction, it cannot move. When I say it cannot move, what I'm saying is, when you move something, you change its momentum, but the second momentum state is not accessible. There's only one momentum state in the Z direction, so that is arrested. The motion is arrested in that. Don't think that it's a particle which is tightly held there. That is not the analogy here. Analogy is the electron does not have a freedom to change its momentum state in the Z direction. It actually can change its momentum state in the X and Y direction, in the plane. Okay. So that is situation is called a two-dimensional electron system or two-dimensional electron gas, or in short, what we call as a 2-DEG. Okay. Now this quantum well heterostructure, in this case, it's a gallium arsenide and aluminum gallium arsenide. This is a typical growth sequence. And here what you're seeing is the conduction band edge through the system. So you have a gallium arsenide capping layer that is just to prevent oxidation of the aluminum gallium arsenide layer. And there is a thin remote doping layer in the middle, which we have seen in the previous slide, and that represents this positive ions here or positive ions here. That is this one. And then this interface, which I have shaded by green color here, that is where the electrons is going to end up. That is where the well is going to get formed. Okay, I have drawn the well now 90 degrees from top to bottom. Now you will get a two-dimensional sheet of electrons here, and there is a dopant layer sheet here. Okay, and this conduction band offset here can be like few hundreds of milli-electron volt. That is room temperature is 25 milli-electron volt. Okay, so you can have this quantum well formed even at really higher temperature. Okay, so this is the simplistic picture of how the two-dimensional electron gas is formed. The dimensionality comes from the confinement is a direction. Two-dimensional means the electrons are free to move only in one dimension. Okay, only in the XY plane. They are confined in one direction. They are free to move in the other two directions. That is the two-dimensional system. All right. Now, these two-dimensional systems are like, capacitors. When you consider some kind of electrode on top of it. So what you have is, you have a sheet of electron in the middle, which I have represented with green color here. Now if you put some metal gate on top, okay, then this metal gate and this electron gas, the sheet of electrons, they together can form like a capacitor. So whatever voltage you apply on this top plate with respect to the electron gas can change the carrier concentration, which is delta ns, which I have written here as the change in carrier concentration, which is proportional to this gate voltage. So now, one crucial information that we need to understand, or I need to note here, is these are two-dimensional electron gas, and the metal that we put on top generally are Schottky gates. Remember that also we discussed, because the gating depends on the strength of the Schottky barrier, and Schottky barrier is there only in one polarity. When you apply voltage only in one direction, other direction it will pass through, the current will go through. In one direction barrier will grow, other direction your barrier will shrink. Okay, or the charge will start going through that direction. So then it's no more a barrier. Okay, it's no more a gate, because gate is not supposed to inject any current into the channel. Okay, so this is what I'm trying to. This is not really an ideal situation for electron system. So electron system, what you will be drawing is, you should draw this way. Okay, so you should apply negative voltage, then you can actually reduce the carrier concentration here. Okay, this is the formula for it. So if you apply voltage on certain shaped gates, for example, here this is a picture of a gate pattern which defines something called a quantum channel or quantum constriction or quantum point contact, which is a topic of our discussion sometime down in the lectures. Okay, So if I apply voltage on this gate here, this is a cartoon. So I have this gate here, there's a gap in the middle. You apply negative voltage on those gates, then you will deplete the electrons right underneath the gate because of the electric field, because of this effect here. Okay, so there will not be any electrons in this region. Okay, so these electrons are gone. There are no electrons here. Okay, and there will be electrons only in the middle. So you got a sheet of electron which is going to reflect the size and shape of the gate on the surface here. So whatever the gate size and shape which you have on the surface, you will get a configuration or shape for the sheet, electron sheet corresponding to that. So this is called electrostatic shaping of the TODEC. That means you are not really shaping anything on the electron gas on the sheet, but you only put gates with a certain shape and apply voltage, and you will get a mirror image of those shape in the sheet. That is called electrostatic shaping. So if you deposit gates in the nanoscale, for example, here what you have is in 500 nanometer, that is a scale. So you get a 500 nanometer construction. If I deposit a gate of this shape, which is what we discussed, okay, gate of this shape, then you get in the sheet of electron, you get electrons here, this, and you get electrons outside, but no electrons inside. Now you got a annular region where there are no electrons. In contrary, you can make another gate pattern. Say the gate is like this, gate is here and gate is here, then you will get electrons in the middle. You get a ring of electrons in the TODEC, in the two-dimensional electron system. So whatever shape that you are, whatever the shape you have on the gate pattern, you get a mirror image of that. But you have to remember that you are going to apply only negative voltage, because the negative voltage is going to give you the Schottky barrier, and positive voltage is not really preferred for a two-dimensional electron gas, because that is going to inject carriers. Okay. So this technology is called electrostatic gating or electrostatic shaping, and that is probably the technology that all the quantum devices on two-dimensional electron systems are actually made. And these are made by microfabrication technologies, techniques, lithography, and other clean room processing techniques that we will briefly mention in one of the coming lectures. So what we have done in this class is the importance of mobility we looked into, and the dimensionality and the formation of a two-dimensional electron gas, and how we can form nanoscale device just by applying voltage, that is electrostatic shape. There you are not going to chop down any material, you will still have the large piece of your wafer or material, but what you will do is you deposit gates on the surface with required shapes, and that will result in the nanoscale devices with nanoscale structures of the corresponding shape. All right. So in the next class, we will look into some of the technological aspects of building. How do we build these devices? Then we will move on to the physics of transport in 2 dimension. All right.